awake. So anyway, yeah, so thank you very much. And we'll we're pretty much right on time, so we'll continue on to our next presentation, which will be Pierre Lemay, who is here from Montreal. Yeah, thank you very much. Okay, so let's get your presentation up here. Okay. Okay, so you're familiar with Zoom and how it all works. Sort of.
Yeah, kind of. Can you get the volume of your computer down?
Yeah.
Because I've got some elevator music, which when I hit the, yeah, bring that down to like 20 or something. I want to talk over it.
Okay. All right. So that's good to hit that because everything works better. And okay, so we'll go back to Zoom and then share. Click on that. Share there. Okay.
And just minimize those windows on the back.
Yeah. Come on. There we go. All right. You can hide that. Push this down over here perhaps.
Yeah.
Okay. All right. All here.
Okay.
Okay, here we go. Everybody, Pierre's about to begin.
Okay, folks, we'll start. Okay, so I wanted to talk about my 20-inch telescope, tracking ball scope, because it's kind of unique as an instrument. It's one of the largest ball scopes ever built. I think there's at least another one, I think in Hawaii, a 20-inch ball scope. There have been other ball scopes built, even professionally. There were large ball scopes built in France for experiments, but they weren't using quite exactly the same design, and they've been decommissioned since then. So I'm going to talk about the design goals that I had for this telescope, which I built many years ago. Making the mirror, the support, the ball itself, which is quite a challenge, and as you can see, the other subjects there. And for some lot more additional information and pictures, you can go on my website, and I have a lot more detail. This is a summary of some of those details, some of the information on the ball scope, but you can click on that, the presentation when you get it, and you will find more information there. So the initial telescope design goals were, I had a 12-inch telescope at the time. This was in mid 90s, and I was looking for something larger, 20 to 24 inch. I wanted it to be transportable in a hatchback car to a dark site. I was looking for a 75-pound optical tube assembly, which was quite a challenge at the time. Back then, a 20-inch telescope was a much heavier telescope. One-man assembly, I wanted to be able to do that myself. Very important, no tool for telescope assembly. All my telescopes are designed normally that there's no tools. Everything is hand knobs and everything is captive hardware. So I don't have to put little bolts in a bag and lose them when I get to the site because or forget them or something. Everything has to be in 1 or 2 units and that's it. I was looking for equatorial tracking. I wasn't sure what design it would be, what the scope design would be at the time. Ended up being a Newtonian, but that wasn't obvious at first. Flat-footed observing, I was hoping to be able to have a scope that would not require a ladder or maybe just a stool, and a rotating tube, which I used a lot. The 16-inch telescope at our club in Ottawa, Canada, had a rotating tube, and I thought that was really neat. It had a rotating upper end. I wanted some kind of way of placing the eyepiece in a comfortable position. And I wanted a 2 eyepiece turret, which also this 16-inch club observatory a long time ago when I was in Ottawa had that, and I'd seen that on other scopes, and I wanted that as well. So there were many other design goals, but these were some of the main goals that I was looking for. So I ended up building a Newtonian telescope, and it ended up being a ball scope, but that wasn't obvious at first. And it ended up being a 20-inch because I found a 20-inch there were want ads in Sky and Telescope at the time. This is in the mid-90s, and a fellow some of you may have known, Dick Nelson. He was the owner of a company called Optical Craftsman. They made telescopes that they sold to amateurs and maybe observatories, I don't know. And he was going out of the business, and you can see a picture of my daughter, my 2-year-old approximately daughter at the time, sitting on the blank when it got to my place from California. A lot of the glass was removed, and this is a bit unusual, was removed for grinding by well, first of all, I'll just talk about the back of the blank. If you look at the picture on the right, you can see that the edge thickness on the right side of the picture is a little thinner, about a half-inch thinner than the left hand. So when I got the blank, this was like, it's as if the blank had been cast, and with the mold was a bit canted, and it ended up with the glass being, the mirror was not symmetrically the same all around. So the first job was I had to remove that glass, and I did that by grinding with a small tool and bring it down to a half-inch thick edge at the back and equal all around. That was one thing, and the next step also was to build a grinding machine. I used at the time, I didn't know about some of the more common grinding machines that people were using at the time. So I saw the article by Donald Dilworth in Sky and Telescope about his relay lens telescope, and he had a basic, really simple design. So I just copied that, and I built that as a grinding machine. It evolved since then. It's become much more sophisticated today, that machine. And also at the time, by the way, just something I want to mention is that at the time I was looking at building a relay lens telescope similar to what Donald Dilworth had built for a 20-inch. I thought it was a nice compact scope. I'd looked through it. I'd used that scope at Stellafane, and so I corresponded with Donald at the time, and he actually came up with some improved designs. And I was looking to build a scope where I would be able to observe from inside, kind of like have the scope outside and with a relay lens bringing the eyepiece in and observe from the warmth of an observing room, for example. That was the initial idea. It ended up, I could have gone that way, but it felt too complicated. I had to make a couple of relay lenses. He was willing to help me along, but eventually I chickened out and I decided on a normal Newtonian. But as you will see, the project became more complicated eventually anyway. And you can see in that picture on the right where I trepaned a hole in the center of the mirror, a 3.5 inch diameter hole, which is where the mirror would be supported. There's a 7-inch flat portion on the back, and then it tapers off to 1/2 inch for the 20-inch mirror. And that's how I did the preparation for the blank for grinding. The next step was curve generation, and okay, this is where I don't know where I got this idea, but this is a little weird. But I went to a tombstone maker and brought a template with the proper radius of curvature, and I said, "Could you sandblast this mirror to give it this curve approximately?" And he was like a cousin of mine, far reach. I didn't really know him, but my dad said, "Oh, I know a tombstone maker." So I went to see him, and he did this for free. It took him 20 minutes, and he went from flat to F4, F3.8, or F3.9 with just sandblasting, and he would put the template around it. And I said, "Be careful not to dig a hole somewhere too deep. Don't keep your sandblasting there too long." And it took 20 minutes, and the mirror was F4, F3.9. I think I was hoping for F3.8, but and then I smoothed out that curve with this small motor turning at about 150 RPM with the same pipe that I'd use for trepanning, and some 80 carbo, and just kind of Blanchard curve grinded my way to a roughly sub F4, F3.9, somewhere around there curve. So that's how the mirror was prepared and rough grinded, curve generated to get the shape that I more or less wanted. The next step was to well, do a good grinding, rough grinding, fine grinding, and for this I used my machine that I had built. Built a cement, Portland cement tool, about 2 inches thick, very heavy. Glued some of these tiles that we bought at Wilman Bell at the time. These ceramic tiles, and the mirror and all the work. And I knew at that moment that all the work had to be done mirror on top, at least for rough grinding, polishing, because it would be that would keep me kind of away from astigmatism. If I tried to work it with the mirror upside down or with the tool on top, it would have been difficult to support the mirror and get support it without distorting it, because it's kind of anyway. So I applied the same thing that we're doing with meniscus mirrors 20 years before I even knew of meniscus mirrors, and I did it this way to try and keep the mirror from being suffering from asymmetry. I I'll talk about it, but I did end up with some astigmatism anyway, but I didn't really know about it. So due to the mirror's central perforation, when I polished as Donald Dilworth had suggested, I just removed the pitch from the area around where the hole is, and just polished away that way, exactly like I did here. Parabolizing was done with sub-diameter tools. This time, after grinding, polishing, making sure everything was okay, I turned the mirror upside down. That diagram on the bottom left shows how the mirror was pitch blocked. I think that's the expression, using pitch to block the back end of the mirror to a pipe flange. And I had a pipe coming in through the turntable spindle was basically a pipe with just an ordinary thread at the end, and the mirror was glued for about 1.5 years with pitch to this flange. And whenever I needed to polish or test, I would just grab the whole glass, unscrew it, and then place it on the test stand vertically, do my test, and then pull it back, re-screw it onto the spindle, and keep polishing. So I used a number of sub-diameter polishing tools. If I had, and I will be doing it again, but when I do it again, I will make a larger tool than the 8-inch tool that you see on this picture. The problem with say a 12 or a 14-inch tool to smooth out the curve was that I had this hole in the middle, and um, I didn't want to, when I was pressing, I didn't want to create a lump that would then damage the surface. So I, yeah, but today I know that I can match a larger tool by pressing it at different locations around the glass when I'm doing the cold pressing, and then start working on it, or maybe just remove the pitch like I did with the large full-size pitch tool. So that's how I parabolize the mirror. Using a Rosnell lens, I got one image. I think the best image I have of this. Too many lines. I could do it again. I could take the mirror out and test it again with much better technology than I had at the time. I have better technology today, but at the time I used the Rosnell lens. You can see that there's a turned down edge or turned edge. Turn down edge in the case of the outside edge. It's about 3/8 of an inch wide. And of course, there's a turn down edge around the hole, the central perforation. But that's hidden by there's a nut, a 4-inch nut that covers that 3.5-inch perforation, and that's not an issue. But you can see that it's very smooth. But what this doesn't show is that there is astigmatism. So this telescope is not very good on planets or double stars or high power stuff, because it's the moment you go above 200, or even when you just try to focus, you can see that there's astigmatism in the mirror. And so I'm looking forward to retesting the mirror with all the new equipment that I have today, and the new test methods that have been developed over the years, including interferometry and all that. This is basically an F4 mirror, so this can be easily tested with all of those techniques, and that's going to be a goal in maybe 2 years from now. One of the questions that I asked myself when I saw the astigmatism was, is it due to my polishing or problems, or polishing errors that I might have made, or was it due to the actual mirror bending? Because there aren't that many conical mirrors that are used by amateurs. And I mean, we have a lot of conical mirrors up to 14-inch in Schmidt-Cassegrain telescopes. But for a mirror this large, it's not that thick. It's 2.5 inches thick. When I started out, it was 2.5 inches thick minus the sagitta. The question was, well, is it deforming? Is it deforming because of under its own weight, and as you move it in a certain angle, is it creating this astigmatism? And so I had a friend a work colleague who did a lot of finite element analysis, do the math for me. I'd done that in college many years ago, but I wasn't able to do that today. And following his modeling, I'll summarize this, but basically, we had a discussion on cloudy nights with a bunch of other people, experts who did finite element analysis as well, and optical engineers. And we concluded that blank had sufficient strength, but when it does deform, it would deform into just another parabola. You just refocus, and it should be the case. But in a recent Cloudy Night thread, we had another discussion with other people, and it's not quite clear. I'm not sure how much astigmatism is generated just by the fact that this glass is the shape it is. We know from Dilworth's experiments with his 16-inch that it was okay, but we also know from Mario Mata. He's an astronomer on the East Coast, and he's built a 32-inch relay lens telescope. mirror professionally made, conical mirror with a very complex shape. It's also conical, the back is conical. And in this CN discussion, we found that his mirror did deform, and they had to add a skeleton support near the center of the mirror to keep it from deforming. Not deforming that much for astigmatism, but maybe a quarter wave or something, and he didn't want that, so that he had the mirror support modified. So I don't know about mine. There's still questions that I need to answer, and that will come in a couple of years when I rework this mirror. Now, the mirror support and collimation is very unique. As I said in the first slide where I talked about the objectives, and I wanted this to track, and I wanted it to be, I didn't want the eyepiece to be too high, so I wouldn't need a ladder and all this. So all of this meant I needed to have the mirror as close to the inside hemisphere as possible, but I still needed to collimate it. And I couldn't drill holes under the hemisphere because the telescope tracks, and I'll talk about this in a minute or two, but the hemisphere had to be whole and not perforated. So you can't just stick an Allen wrench through the back and collimate from the back. I had to collimate from the front. And since I had a perforation, I said, I'm going to use that perforation. And you can see here on the, you can see on the bottom drawing, the bottom left drawing, how the mirror, the basic idea is that there's a thick aluminum plate at the bottom that I'll show you how that is attached to the hemisphere, which is basically the base for the collimation of the primary mirror. Now I have three, you can see on the pictures on the upper right, you have approximately 3-inch diameter gears that mesh with a spline, which is attached to rods that go through the mirror and stick out up on top of the mirror. When you rotate one of these splines, it rotates the large gear, the 3-inch gear, one of the 3-inch gears, and it moves, and that gear is attached to a fine threaded bolt, which bolts into that large plate. So when you rotate one of those splines or one of those extensions, that gear is rotating and it's lifting the mirror up on one of 3 sides, and that's how you collimate. And then there's a central bolt, which you can see on the left picture in the center, which when you finished collimating, you tighten that bolt down, and it locks the whole mirror support system to the position that you've collimated it to, and the mirror is free floating in this aluminum support. So that's how I collimate. By the way, just for the fun of it, those 3 aluminum gears, I couldn't find anything on the market that I could put a screw through it and everything. So I had to build those, and I hand cut the gears on those 3 large spur gears, or large spur gears, by printing if I needed, I don't remember how many teeth there are on there, but say I needed 60 teeth, I would print out with AutoCAD a paper with 60 lines on them, stick them on the aluminum blank, which I would have cut on my lathe, and then using a hacksaw, I would just cut until I heard the blade touch the paper, and then move to the other one and kind of align them approximately, and then use a file to make the little gear teeth, and it worked. And it took about 20 minutes per gear to do that, and that's how those gears were cut, and they still work today. The splines were. I have no idea, and I don't care. The interesting thing about this as well is that, and I'll show you how the plate is attached to the hemisphere, but once that's collimated and locked in, unless you remove the mirror for cleaning or whatever, you never need to retouch that. That collimation of the primary mirror never moves. Doesn't mean it's perfect. I'll talk about that, but it never moves. It's amazing how solidly attached it is to everything. Yeah. The radius, yeah, well, the way I did it is you mean like the bolt heads that stick out and that touch the plate where the mirror? No, because it's flat. Yeah, there's a 7-inch flat on the back of these conical mirrors. So it's sitting on that flat. Yeah. And then
With that radius, does that have an effect on FDA?
I don't remember. That was 15, 20 years ago, but I don't think so. I think the way he built the model is he assumed that was like a foundation fixed position. Yeah. You had a question? Okay, just stretching.
Yeah. Comments later.
Okay, okay. So the collimation, it says collimation on top there, but anyway, collimation, how I do it. So I collimate from the top, which is really an advantage. And because the mirror is perforated, of course, I can't use a laser that will, with a little a ring on the mirror, because there's no glass in the center. There's a hole. The mirror is perforated, and there's this unit that holds the mirror. So when I want to collimate, I have to use a star. So the secondary mirror is first collimated. That goes out of collimation when I move the scope around. I have to always recheck collimation of the secondary mirror. So it's collimated with a laser. I just put a normal laser in, make sure it hits the center of that large bolt at the bottom. And then I remove the cover of the mirror. I place these extension 3-foot extension rods, which you see here in the middle. The arrow is pointing to them, and when the telescope is looking roughly up, I find a star somewhere near the zenith. And this is a ball scope, by the way. So zenith, we love zenith with ball scopes. So you just move it around. There's no gimbal lock, no Dobson hole. So you just find a star, and you look at the star in the high power eyepiece, and you rotate those extension rods, which are connected to the little bits that come out on top of the mirror. And everything is designed that if I drop one of these extension rods on the mirror, there's a Teflon or a nylon white, that white thing will not scratch the mirror too much, I hope. But I've never dropped one, and I'm very careful. And of course, like I said, I do that once, and once it's done, I don't need to redo it again until I remove the mirror for some reason. And so I look at in the high power eyepiece. I do my collimation. What I do normally is I place the collimated star wherever it goes, on the left edge or right edge, or where I can see that they're all collimated, and then I rotate those screws until I bring that image to the center of the eyepiece, lock it down, and that's collimation. Now, there is a problem with the collimation, and it has to do with where those bolts, I think in this bottom left image, where those bolts here touch there's a flange here where the mirror is sitting on a flanged plate, and the bolt heads push on that to do the collimation. But when I tighten the bolt down, the central bolt, there's a bit of movement there, because if I had a thicker plate, I could insert a tight fitting rod that would then have threads, and it would, it wouldn't move much, but because it's a bolt, there's a little bit of movement, and it's kind of unpredictable. So when I lock it down, I can see that the collimation goes off a bit, and that's a problem. And Mirror's got other problems, but that are worse than this. So it's something that I would need to improve. So there's a slight mirror shift. One of the future improvements, because this is a six, the truss tubes are a six truss tube arrangement. I can change. I could add a collimation by by changing the length of the truss tubes. It's a Stewart platform type arrangement. And that's something that I'm considering doing in the future for fine collimation. Don't know if I'll go there yet, but it's certainly a possibility that could easily be added to this design, easily be added to this design. So that's how I collimate. Now, how I made the hemisphere, the ball. What am I doing? Yeah, the ball scope was that ball that holds the mirror is a 30-inch hemisphere, 30-inch diameter by 3/16 inch thick. The skin is 3/16 inch thick. It's made of short glass strand epoxy putty, like Bondo, I think it's called. And it's then topped with 6 coats of, I think half a dozen coats of liquid epoxy resin. The diagram on this page shows how I came up with the idea of how to make the hemisphere. This was the second try. The first try, I tried something else. You can go and see it on my website, but it wasn't successful, and it created a hemisphere that was very heavy and thin on one side and thick on the other, and it just wasn't doing well. So I needed a substrate that was the proper diameter, and then I could apply an equal amount of and thick enough amount of putty to that to make it solid enough. So the way I did it was to first I pre-cut some styrofoam, those 2-inch thick styrofoam insulation that you use for homes or basements, and I bought those, cut them off roughly the angle I wanted. And then I built this using just an ordinary workmate type support. I mounted a pipe that went through all the layers of styrofoam and attached to that plate that I showed earlier, that thick plate that supports the primary mirror for collimation and everything else. So when I could then control the angle, and I had a router with a bit on, just a flat bit on the end, so I could control the movement in an arc in one direction, and I could rotate the whole styrofoam structure and putty eventually with the other hand, and just take cuts and then apply some more putty and just build up the thickness that way until I got the sphere I wanted. So you can see in this picture the first part of that. On the left picture, you see the router there mounted on this jig, this sphere making jig, and on the right picture you can see the plate here on the left here is attached. You can see the bolt just sticking out in the center, which is connected to a pipe that goes all the way to the bottom of the, you can kind of see it here. There's a plate at the bottom. There's a pipe that goes through it and attaches to another piece of wood at the bottom. So this is how that was my axis of rotation in one direction. And to cut, I had the other axis of rotation perpendicular with the router. And you can see that on the end of there are some nuts here where that are attached to bolts that are attached to the plate. And those are the anchor points. I wanted to make sure that once the whole thing was built, I wasn't just relying on the Bondo glue gluing to the aluminum. I wanted a solid attachment point so that I didn't want the mirror falling out of the scope with the plate coming off with it. So I added these anchor points, and I applied putty. So you can see on the left picture, there's the router on top of the styrofoam. You can see the plate that's there, and you can see how much putty I had to add there. In the middle picture, I'm adding the putty with a putty knife, and by the way, styrofoam is eaten away by epoxy, so I had to cover all of the styrofoam with just some 2-inch wide tape used for when painting your house, or gaffer tape, I think it's called. So I just added tape just to make sure that no putty would touch the styrofoam, because that would create a hole in the putty, and I would have to put even more putty to fix that. So the hemisphere at this point, you can kind of see it in the third picture, is covered with styrofoam, and so I would add the putty all around this plate, and then I would take cuts with the router, and I would do the same with the applying putty over the whole surface. The bottom part was also had a wooden. The whole styrofoam stack is sitting on a 3/4 inch thick plywood plate, and I had little wood things sticking out on the side everywhere, so that that would anchor that as well. And then I would just cover that with putty, take cuts below, above, and eventually in between, until I made the hemisphere. And the last step was to I took this outside, and I removed the whole hemisphere from the vertical position it was in, placed it horizontally, added a heavy chuck at the other end, and a couple of nails in the wooden plate, which you can't see, but it's on. I'm turning with my hand, and I would just add some resin with some colorant, some dye in it, to create the hemisphere. And I would just rotate. I would apply it, rotate until it started to gel, started to polymerize, and then I just let it dry out, sand it a bit, and then add another coat and another coat until I had a satisfactory color to it. And then in the end, I cut that plate that I had at what was at the bottom, now is the top, and I just cut that away with a jigsaw, and removed the styrofoam, which made quite a mess, by the way. With just a knife, I cut away the styrofoam and just pulled it out, and I ended up with a perfectly formed hemisphere with the steel plate, the aluminum plate in the bottom, ready to receive the mirror. So that's how the hemisphere was built. But then I realized that if I wanted to attain my goal of a 75-pound optical tube assembly, I wouldn't be able to do it with this. The hemisphere was way too heavy. And I kind of realized at one point that I didn't really need this part of the hemisphere. So to reduce the weight, I decided to cut away part of the hemisphere, which is not really required. If you cut away this section here and you mount the telescope like this, you move the center of gravity of the hemisphere to the right, and that's offset by all the equipment that you put on top of a telescope, the eyepiece, the finder scope, the controls. You end up bringing it back towards the center. If you don't do this with a ball scope, because a ball scope has to be balanced up and down, but it also has to be balanced around its optical axis. If not, the eyepiece and everything will bring it always towards the bottom. So the way to solve this normally is you add weight offset on the other side near the mirror. You will add lead shots or something in epoxy. That's how they do it normally. And I looked at it and I said, I don't even need that stuff. And it's going to reduce the weight quite a bit and bring me closer to my 75-pound optical tube assembly weight. So this project, by the way, was a risk from A to Z. I mean, everything that I did here, I had never seen any of this stuff done, whether it's I had never seen it done. I know it's been done, but trepanning a hole in a mirror, reducing the back end to make it more symmetrical, using a sandblaster for a tombstone maker to grind the center. All of this was risky. I didn't know what I was doing, but I had confidence in myself. So I did it anyway, and this was one of the risky things. Is I had spent 100 hours making this thing, and I decided to cut it up. And so I mounted it on a large ball bearing that I had acquired somewhere, and put some cement bags in the middle of the hemisphere to weigh it down. Mounted a felt tip marker, and rotated it. And I was amazed when I wrote to mark the cut line, and I was amazed how the tip of the felt marker never left the hemisphere. It was that accurate. It was really round, and all around the mark was perfect. It was exactly it was quite round. And then so I marked the cut on the left image, and then on the top I just used a jigsaw again, and I followed the cut line, and I built a new top reinforcement ring to receive the tubes, and that brought of course the weight down. This weighed about I must have cut about 15 pounds off, plus maybe 5 pounds of counterweight. At least 20 pounds were cut by doing this. It also brings the mirror closer to the outside. One of the problems with ball scopes is that you're placing a mirror in the bottom of a tube, and you can't put ventilation, not with if you want equatorial tracking the way I did it with this. So by doing this, I was opening up the tube. It was easier to ventilate if I needed to, and that was one of the other reasons why I felt it would be a good idea to cut that away. So I did this, and I got the hemisphere that I wanted. Would I do it again today? No, I wouldn't do it again today. There was a lot of work, but I found this company recently, a couple of years ago, that sell these acrylic domes made of up to 60 inches. I think they make them in all up to 69 inches and up to half-inch thickness, and they vacuum form them, I guess, and they sell these, and you can buy them. They're made in the state of Maine, and there's a Canadian. They're just across the border from Canada and New Brunswick, so you can also order them from their warehouse there. And you can get a 30-inch for about $300 maybe. And then, of course, I'd have to find a way of attaching that plate to that, but that's a relatively minor problem. So if I had to do it again, this is where I would get the hemisphere. Okay, now the upper tube assembly is more conventional, although there are a couple of things that are different. The end rings of the you can see on the image on the right, the end rings are made of bicycle rims that I found that had a 21.5-inch interior diameter, whatever outside diameter, and to reduce weight, I used my milling machine to cut slots, and I have a 2-eyepiece turret, which I'll talk a little bit more in a second here. I have spider vanes that are made of, I don't know if I can get this. Here. I have spider vanes that are made of 10 thou thick shim tool, stainless steel, and they are used to transmit the power the diagonal heaters. I don't have a wire going through it. One of the sets of the vanes is plus 12 and the other one is minus 12 volts. So or plus and minus for 12 volt. And they're connected up to the Kendrick heater that I use for heating. So I have the Kendrick heater. I have the Quinsight, which is similar to the one that's on the scope here, which you can see mounted here. It's mounted on top of the eyepieces. In a ball scope, you can use a ball scope either on the left or on the right side, because it's a ball scope. So it's not like a Dobsonian where you're always observing from the left or from the right, depending on where you placed your eyepiece. So this in this design, I placed it right in the center, just on top of the furthest end ring, and I can easily look at a star when I'm searching, and then I rotate my head and the eyepiece is right there. So it's very practical to do it that way. There's also a SkySolve picture with a SkySolve camera, which Pi 4 plate solving camera designed by Dale, which I'm working hard at getting to work. It's getting there. And I have a bit of a weird mount, which I don't like, that's attached to the bottom end ring. I need to improve that, but if I don't touch after I collimate the camera, it works quite well when if I'm not using it with an Apple computer or Apple iPad, because it tends to lock for some reason. But I found recently that we're getting good results with what's it called, when it's not an iPad, it's a Android. Thank you. Seems to be working better with Android. I've got a light baffle extension, which you can see on the bottom here, which stores, when I'm storing it, I just remove that and I attach it to the upper end. It moves off to the side. And the whole upper tube assembly, when it's taken apart, nests inside the hemisphere. And I also have an Aurora filter system, which is exactly the same as the 28-inch, which is here. So
focus with that turret.
these are helical Crayford focusers that I made.
You have two focus.
Yes, yeah,
Oh.
there's a double. The bottom eyepiece is the one you're observing through, and the top one is storage. And it's very normally you have a wide field eyepiece. I have a 21 millimeter Explorer Scientific 100-degree eyepiece with a coma corrector, the MPCC coma corrector in this case. Okay, so I'll try to finish this so we can go to lunch. So I'll go to the truss tubes. I think I had finished. Yeah. So we'll go to the truss tubes. The truss tubes are 6 1-inch diameter aluminum truss tubes, anodized. They were from Moonlight. Moonlight used to sell those. They don't anymore. They're color coded, as you can see. I have a little yellow ring here, and I put yellow or red or blue on each of them. And you'll notice a little something different about they attach at the top, and they attach one on top of the other instead of sideways. It just seemed like a good idea at the time, and it is a good idea. It works quite well. And they're attached 2 by 2. So that's how I did it, and it works. Not too much to say on that. The bottom section of the tube has a threaded rod with a ball at the end. And initially, the hardware was plastic, but it dried up and broke up. So I found these copper pipe hardware at Home Depot, which worked. I need a little bit of machining, but they work quite well. And they allow me to adjust the length of the poles, of the 6 poles, to bring the focus, to optimize the focus at the top. And I found I build all my telescopes now this way because whenever I cut the tube, it always seems to end up cutting it too short, and that's a way of compensating. And it's quite solid, and and of course it's a universal joint, so it works quite well. Now the two eyepiece turret, I talked about it earlier. You can see it here. This is an early picture, but I made the two. I have a 2-inch and a 1.25-inch eyepiece holder because of the indexing mechanism, which is hard to photograph. It's on the right. The eyepiece must always turn in a certain, like the little eyepiece on the which is on the bottom in this picture, must always swing to the right. Because if I swing the large eyepiece to the right, it'll hit that indexing mechanism and it'll block. So it can't go that way. It has to always, the large eyepiece must always go on the left and the small eyepiece on the right. You get used to it when you're using it. I have a handle in the middle, which I grab for rotation. And I made the two eyepiece holders are homemade helical Crayfords, and they work quite well. You can see on the bottom picture how my head just clears the large eyepiece on the top. I did some tests initially to determine how I wanted to make that as small as possible, but there's a limit because your head has to clear the eyepiece, and that was about 5-inch distance between the two eyepieces. And when I collimate with the bottom, with the 1.25-inch eyepiece because I put a high power eyepiece in there. So normally the top eyepiece, the large eyepiece, is always there. It's part of the counterweight system of the telescope, so I cannot observe without it being in place, or at least without a weight in its place. And I do have a weight that I use when I take this apart and remove the eyepieces. I put a 2-inch brass slug in there just to get the weight. Oh, and one thing, that last comment, the coma corrector doesn't exist for 1.25-inch eyepieces. There's a way of making them using off-the-shelf optics and all this, but Robert Hossein, I think his name is, who created the Houdini set of eyepieces recently, about a year ago. These are coma-corrected eyepieces, no need for a coma corrector, and they're lighter weight, and I'm looking forward to buying the full set when they come out. There's only about 2 or 3 eyepieces out at the moment, especially for the 1.25-inch ones. That means I won't need a coma corrector. I can use the eyepiece directly. And I don't know if anyone here has used them yet, but comments are pretty favorable on their use so far. So looking forward, because for lightweight telescopes, like ball scopes or other lightweight telescopes, being able to not use a coma corrector reduces the amount of weight and the expense that you need, and yet you still have a fairly wide field. These are 82-degree fields, but you don't have that 1.15 time increase in focal length, which you get with the paracord, for example. Remains to be seen how good they are, but if they're pretty good for a lightweight telescope, that would reduce the weight a lot, and that would be advantageous in my case. Because the scope is tracking, even though I have an no coma corrector on an f4, normally that would be a problem, but the scope is tracking, so I can put the position of the object I'm looking at right in the middle, and it won't budge. So it's at least it's optimized for the center of the field. The tracking platform. So back in the early 90s, when I was working on the 20-inch and I was trying to figure out how can I add tracking to this, I came up with this idea, which was featured in Sky and Telescope in the January 1996 issue, in an article called the Top 10 Telescope Ideas of the Year. And I had presented this telescope as Telephane. This picture was taken by the Sky and Telescope photographer there. And you can see the principle of the mount, which is basically with a ball scope, you You use a drive roller or two drive rollers that I use in my case, and a free rolling ball on the other end. And if those two rollers are pointed towards the pole, one of the poles, you will get tracking wherever the scope is pointing, and you can adjust the angle of the rollers to get different latitudes, and it doesn't add any, they're multi-latitude, it doesn't add any height to the eyepiece. You don't need to reset it. It just tracks all night, and they're very simple to make. I've made many of these. Jerry Olton rediscovered this idea about 10 years later, and he's been using it on several of his scopes. So I built a 6-inch prototype, make sure it worked before applying this to the 20-inch, and it worked. It works beautifully. The tracking platform, you can see some of in these pictures. You can see of the 20-inch, you can see the large drive roller, 1.5-inch diameter. There's 2 synchronous motors. At the time, you could get synchronous motors. They provide very smooth tracking, and there's also 2 small balls, which you can see at the bottom there, which will capture the telescope if it comes off of its tracking platform, because there's a kind of an interference between the tracking platform and the tube, which creates a kind of a blind spot near the northern horizon from east to west. It's not, when you're down about 20 degrees above the horizon in the north, maybe 30 degrees east, 30 degrees west, you can't see those objects when the platform is pointing towards the north. I don't have a blind spot at zenith, but I do have a blind spot there. At worst, I just lift the telescope, put it on the ground, and observe it without the tracking, or I wait a couple of hours and I observe it when it rises again. For tracking, the third point of contact, other than those two motors, are a bunch of roller bearings, which you can see here. I could have put a tube with just 2 bearings. It just was simple to do it this way. I thought I had these bearings for nothing, so I just added them. But it would be nice if this third point was also had a motor on it. It would add friction and control, but it works quite well this way, so it's going to stay that way. And you can see at the bottom a picture of the entire platform with those 2 balls at the bottom, which catch the telescope, the 2 drive rollers, and the little ball bearings in front. I used one of these, found these batteries that have 110 volt inverters in them, and 12 volt and 5 volt and everything on it. And they're very practical. They don't weigh much. They give me about 15 hours of tracking I have 2 of them for these 2 motors, and it works really, really well for when I'm on the road. If not, I can just plug it in the 110 volt at home, and that works. Transporting the telescope is done quite easily because the platform integrates permanent. These are large plastic wheels that are used for lawnmowers. They're about 16 inches in diameter, and I added those to the platform. And the handle, which you use, the wheelbarrow handle that people normally use, I use just these 2 rods which push into the frame of the scope at the bottom, and I can both push or pull with this. They lock in place, so I can push them into the car or on the ground without any problem. And you can see the center of gravity of the scope is just above the wheel, so it's effortless. Lifting and pulling this is really not difficult, not effortless, but fairly easily. And there are trees around my house. If a tree is blocking, I can just move it around, even with the drive tracking. When I align it on the pole, I just roughly eyeball it, and that's good enough for at least a half hour of tracking. And if I'm more accurate, the tracking can last hours without interruption. Transporting the scope in the car is done with 2 aluminum rounds, which are just very lightweight U-channel aluminum extrusions, which I bought and attached together. I have a short video, a 5-minute video, which I'll show in the end here, which shows how it works. And you can see I move it. One of my objectives was to move it in a hatchback car, a small hatchback car, and this was at the time I had a Toyota Matrix. It's a small hatchback car, and you can easily push this into the car and be on your way. The scope weighs about 130 pounds. The optical tube assembly about 80. I was aiming for 75, but I ended up with an 80-pound tube assembly, including the eyepieces and finder scopes and everything. So that's a fairly reasonable way to move around. And with the platform on there, you can also see the 2 aluminum, the bottom picture shows them well, the 2 aluminum rods that stick out. That's when you place the telescope in this position, you don't want the scope falling off its drive rollers because that's the only thing holding them. So I add these 2 pins, these 2 shafts to hold the scope so that it doesn't fall off onto the ground. And I remove them during observing because they get in the way. So the future, the mirror needs repolishing to remove astigmatism and scratches. I'm going to work on that after I've done my 28-inch, which is the next project. I'm seriously considering grinding the mirror down from f3.9 to f3.5 to bring the eyepiece really flat-footed observing. Scope balance would be improved by doing this. I would ask Mel if he thinks it's a good idea, but I know what he's going to say. He's going to say it's a terrible idea to regrind a mirror from f3.9 to f3.5. It should be reground to f2.5. But so I won't ask him if he thinks it's a good idea. Eventually, I hope to buy a full set of those Houdini eyepieces and try them on this telescope and other lightweight telescopes, and add hexapod truss tube collimation, like I mentioned, and add a light shroud, which I don't have at the moment. I'd like to show you this little video, which will show you how the scope is taken out of the car and assembled. I'm just going to reduce the weight. I've got some elevator music on there, which I'd like to speak above. So let's see if this works. Why isn't this going full screen? Well, I'll show you this way. So this is our club observatory near Montreal. And these are the ramps that I take out here first. Those small aluminum ramps, that's all you need. They have attachments at the top and bottom, and they have attachments so I can attach them to the car so that the scope doesn't fall off because I don't notice they're slipping off the bumper, for example. So you can see me here attaching those safety lanyards to the car. You can see this video on YouTube if you just type 20-inch f3.9 ball scope. So here I'm pulling out the handle that is used to carry the scope. You can see it's not too heavy. You can see the tube is moving around, and so one thing I found when I was driving around it is I have some elastics that attach this to the car structure because it tends to move around and jump up and down when there's a bump. And when I'm at the location, I just push that in and that's it. These are the truss tubes. They're attached in pairs of three pairs. Nope, forgot to remove the upper tube section. So the upper tube assembly is nested inside the hemisphere. And it's just sitting on the protective cover for the mirror. Get this music out of the way, it's ridiculous. So this is how I attach them. So they're trickier to attach than the plastic ones I had before. They were easier. They had a larger thread, and I don't like these. I always have trouble putting them on. But after a few tries, I end up succeeding.
You get a little bar soap will help.
Good idea. I never thought of that. Yeah. Because these pipe things, I don't know what they're used for, but they're used by plumbers for something, but they fit this quite well. And they never, like I said, all the hardware is attached to the telescope. When I'm carrying the scope, I have to remember to bring the scope and the truss poles. Everything else I don't need. So I don't forget anything, which I've done with other telescopes. And then the upper tube section, they meet together and there's a bolt that goes through, a 1/4-inch bolt that goes through and attaches to the rim. I was afraid that would happen someday, and it did. The aluminum bicycle rims are very thin, and the thread that I'd put on there eventually stripped, so I had to add some thicker aluminum plates that I attach to. So that's the scope is assembled. Then I place the eyepieces, which I talked about a weight that I use. You can see here I'm pulling the weight, the brass weight out. It's about a 2.5 pound weight. And then I place the eyepiece, which rebalances the scope. And that's the drive. So you can see here the scope, how it moves very smoothly. And it doesn't show here, but the moon is just above there. So I was just going to aim for the moon. And I thought, oh, I forgot to remove the mirror cover. So the mirror cover, there's a large knob, which I'm unscrewing here, which attaches to the mirror support. And then I just pull the cover off, and there's the mirror. And there's a big battery that's used for heaters and computers and whatever I need, a 12-volt battery. And here I'm installing the Quinsight. And then I look for the moon. And you can see the eyepiece turret turning here. See? So I'm placing the 2-inch eyepiece in position and then focus, and that's it. That easy. So how do I get back to? Oh, there it is. So that's the presentation. Sorry it took so long.
Yeah, that's good.
Any questions? Yes.
Yeah, great. So, it looks to me, maybe you could chop off the, like, bottom part of the ball too. Like a slice it, cause maybe you don't need it, right? Cause
Which bottom part?
like the ball, we could chop off the, like, a slice of it.
No, you need all of it because when you're pointing, you're rotating the tube continuously, and you need all of that surface that's left is always, depending where you're pointing, east, west, up, down, you're going to use some of that to, and you need it for tracking as well. And the eyepiece is always, you see, when you're observing, you have the eyepiece position, say, is here, and you can bring the scope upside, the eyepiece upside down to a point, and then at some point you're not going to break your back. You're just going to rotate the tube, and you're going to use that surface. You're going to rotate the tube to continue observing with a more comfortable position. So you need all of the surface that's left. I can confirm that. Yes.
I was intrigued by your,
The eyepiece turret. Yeah.
yes, I saw the 3 small bearings, but did you cut a groove in the aluminum disc or something?
Yes, the aluminum disc has a V groove, and the bearings have V grooves as well. I found those somewhere, and I have a stack of them, so I can, if they break, I can replace them. I think they sell those, but they're little bearings with a brass V-shaped, that match the V of the. That's how they're held, and they're very very steady. And I have a rubber ball which rotates, and there are 2 indexed holes. So when I rotate, the rubber ball locks into that hole. Sorry?
Spring-loaded ball?
Yeah, spring-loaded ball. Yeah, and it locks the position, and everything was machine milled on my milling machine in one shot, so it's very accurate. Other questions? Yes.
Lower truss connectors, are they metal or are they plastic? Bolt that holds them down.
The lower metal they're metal today, but they used to be plastic,
Oh.
because these were shower head. When you buy a shower and there's this plastic thing,
yeah.
and you used to be able to get them out of metal. The ball itself is metal, but the rest of the hardware is plastic. And it worked for a couple of years, but plastic in the end dries up and starts to crack, and I have to replace them because if not, the whole scope will fall apart. And I still remember the the lady at the store when I bought 8 of them, because I was going to be an 8 truss too, and she said, "Wow, you must have a big house." Yes.
I'm also really intrigued with your, did you call it a gravestone grinder you used for the curve generation?
No, this was literally, the guy had his nozzle in his hand, and he sandblasted the center to start,
Okay.
and he used that, and he spread it out until he got to.
Okay.
That's how it was drawn. I remember reading that somewhere many years ago in the 60s or 70s. Someone had done that.
Starting to tell article about a 24-inch F4 in Illinois that they sandblasted out.
Okay, that's probably where I saw it, and I said, well, if it works for them, I'll try it.
I did it with a 40-inch at 3.6.
Did you? Yeah.
I had a template, colored, blasted.
It works.
Yeah.
It's very fast. It's amazing how fast.
He's a graveyard guy, he let me in his pit. All right.
There you go. Anything else? Anything else?
Was
Okay.
that before you perforated the mirror?
Yes. Yeah, I did that before I perforated the mirror. And the mirror was not only unequal thickness around the edge, but it was also, it's as if glass had spilled over the mold. There were chunks of glass sticking out. So I used just a diamond grinder and I just rounded roughly round, and then I rotated it and made it as round as I could.
Sorry, one more.
Yeah.
Attaching the center of the mirror, how do you attach your fitting mounted? Are you
Well-
using a bolt on the top, or are you trying to maybe expand into a ring inside?
Well, the mirror is just dropped onto a cylinder which has it's about 3,000th of an inch smaller in diameter than the mirror hole. It's very, it's not tight fitting, but it's because there's expansion. So it just fits, and there's a thread at the end, and I screw a retainer ring that retains.
Surface of the mirror.
Well, the ring is on the aluminum tube, and it rests, there's a little Teflon ring so that it doesn't touch the mirror directly, and it tightens
Just
it.
getting off your statement about putting it on the mirror machine spindle, and I think you said screw it on.
Oh, that's when I was making the mirror.
I think it was a similar amount.
Yeah, when I was making the mirror, I think they call it pitch blocking. Use pitch to block the bottom of the mirror to the mount that was used during grinding. That's another mirror mount. It's a different thing.
mount.
Yeah. And if you ever get a chance to use the scope, those who have really enjoy it, because it's like you're not fighting the tube, especially when you're observing near zenith. Whenever I observe with someone who has a Dobsonian, say, well, we're not going to look there because that's near the zenith. I said, no, this is a ball scope. Go ahead, enjoy. And that's the whole idea of the ball scope. And having the tracking, you just stop and you show someone and 10 people, and it's always there. The object is never moving.
Perfect finder, a perfect candidate for the sky solving too.
Well, yeah, I'm working on that, and I need to get weight down. And what I'd really like is to mount the sky solver eventually at the bottom of the tube. It doesn't really need to be at the top. And I've got my iPad, for example, clipped to one of the truss tubes with a broom handle. The broom handles, when you click a broom handle to the wall. I've done the reverse. I've attached it to the little thing that holds the iPad in its cover, and I just clip it onto the 1 inch diameter truss tubes, one of the truss tubes, and I can see while I'm moving it around. But that all adds weight to the telescope and makes it more and more unbalanced. And
So speaking of weight, I think you mentioned that the counterweights are behind the mirror. Do you have to remove the mirror to change the counterweight?
I don't need to remove them because I have about 8 pounds of counterweight behind the mirror, little pieces of brass plates that I've put on, because initially it was balanced okay, but then I started adding finders and other things and filter wheels and of course it's a 1-to-4 approximately ratio. So whatever pound I add up there, I have to add 4 pounds down there. And so I don't need to remove them because they're average okay. But sometimes if I have a heavier eyepiece and I'm observing, especially near east or west, then I'm in the axis of those bearings, those ball bearings. I don't have as much friction to hold it. And because there's no friction adjustment on this, you get what you get when you sit the scope on the 2 drive cylinders and the third free rolling ball bearing. So you end up with what you get. And sometimes if it's too heavy and I'm observing with a low power eyepiece, I'll remove one of the high power eyepieces, and that's enough to just bring it back in balance. But it would benefit from another pound or 2 behind the mirror, but I'm going to shorten the tube and redo the whole thing. That'll change it. Okay. Howard, I think I'm finished. Thank you.